Good morning, everybody. Today I'll be covering our efforts in a 5-year project to create a full flow for EDA tools for superconducting electronics based on the Josephson junction. Given the time constraints and the number of my slides, I will keep my talk to the key points and to the key levels, and I might even choose to skip a slide or two here and there to just focus on the key points. So the motivation is simple: the sudden interest in a technology that has been around for over 50 years. So as you can see from Intel and AMD, the CPU clock frequency has stagnated, and for a good reason. The reason really is power. So if you look at the benchmark system in terms of how much we are consuming energy and versus the target of the system versus the thermodynamic limit of how low you can go in energy, you can see there is a factor of 1,000 between the target of the system energy and how much we are currently consuming per bit. In fact, if we stay on our current projection, even with the clock frequency stagnant but doing parallel processors, we're going to need more energy than all the world capacity to generate power, so that's a problem. So superconducting electronics promises to take us close to the 10 to the minus 17 joules per bit, which is the target. So there are various families of superconducting electronics based on the Josephson junction. Our goal in this project is to reach a VLSI integration level of 1 million gates and 10 million Josephson junction devices to demonstrate it in a 32 or a 64 processor. Our choice is, of course, ARC, since it is our Synopsys processor with a frequency of over 100 gigahertz. The families we are pursuing, there are 4 famous families we are pursuing. The first 2 are really one and the same with minor changes. This is RSFQ, stands for Rapid Single Flux Quantum, and the ERSFQ is just the energy efficient one using a Josephson junction to limit the bias current. Also, we are doing AQFP, which stands for adiabatic quantum. The adiabatic quantum is a low frequency. It's roughly 2 gigahertz, but it is extremely energy efficient. It uses 4 clock cycles. It has its own techniques, but there are no DC currents in it at all. So it is the most energy efficient of all those families. Okay, so what is our starting point? I've created this simplified flow that we've used for many, many years for ASIC and system on a chip. It starts with specification, high-level design, simulation, etc. You're all familiar. If you've done any CMOS design, you're familiar with this in terms of the full flow, starting with synthesis, verification, place and route, fabrication, etc. So in general, the superconducting electronics flow rhymes with CMOS, but it has various differences. The first difference that should catch your eye is that the Josephson junction is a 2-terminal device versus the transistor, which is a 3 or a 4-terminal device. So it has no voltage gain, which means you are restricted to a fan in equal fan out equals 1, which means if you want to propagate a signal, you cannot have a fan out, so you're going to need splitters. Also, power delivery is extremely difficult and tricky in the following sense. You have to bias every Josephson junction in the design at a certain limit related to what's called critical current. Above that, it goes into resistive region and it's of no use to you. So now when we are talking about VLSI integration, theoretically, if we don't have design techniques that would alleviate the power delivery problem, think of this. Think of a chip with 1 million gates, 10 million Josephson junctions, that is going to need a bias current of 30 to 50 amps delivered at roughly 100 to 150 microvolts. That's a huge problem. It's not trivial, so you have to have techniques for realizing that. The other thing, an area that's still lacking big time that we hope to borrow from CMOS, and we have a lot of knowledge in it, is DTCO and DFM. DTCO, which I will be stressing a lot in my talk, stands for Design Technology Co-Optimization. It's a technique or a methodology to short the duration needed to develop a technology from, let's say, a year to less than 3 months and so on. And DFM stands for Design Manufacturability design for manufacturability techniques such as OPC and whatnot. In the literature, you see very limited use of OPC for square Josephson junction. It takes us to where we were in CMOS at the onset of OPC at 90 nanometer. So there is still a lot we can gain from that. If you get nothing from this talk except this slide, you've got the whole talk. What it's all about, I've put it really categorically. I've created this to put DTCO, which I've mentioned a few minutes ago, Design Technology Co-Optimization, at the very top. What it stands for is the following. We are creating add-ons for every single tool in the CMOS flow, starting with TCAD, spice modeling, library development, RTL synthesis, etc. I will not enumerate them. And within each category, I enumerated a lot of tasks which we are doing. And again, it rhymes with CMOS, but it's a little different. So what is this DTCO and what are those two subcategories doing? Essentially right now, as well as in old CMOS, you start by a certain TCAD models, you design your process, you fabricate some junctions, you fabricate some basic circuits, extract the silicon, modify the process, and so on. Every cycle is 3 months to 6 months. Here, what we do is start with ab initio, essentially basic physics, just very preliminary equations, generate what-if situations. Based on that, do spice modeling, including Monte Carlo variability, take it through the full library development, and also take it further through a full design cycle. And based on this what-if scenario, with the spice model distribution, it gives you feedback as to what is your best material of choice, what tweaks you need to do to the process before you even fab any silicon. And again, sometimes, so first in the TCAD, spice modeling and library area, I put it under the name technology preparation. It gives you a short circuit in terms of knowing what technology direction, in terms of materials, in terms of design rules, and so on, you're going to go with. Having done that, that's not enough, because sometimes, and we know that also from CMOS, by the time you take it to real designs, that's where, with the loading, with the fan out, with everything, that's where the surprises come. So we have another loop, which is implementation refinement, and the two loops talk to each other. And this is, in a nutshell, what it's all about. And this is what we're adamant at doing. More focus on what is included in each cycle in terms of DTCO. I will skip that for the sake of time. Layout versus schematic. I will jump beyond layout versus schematic to essentially what I would call front-end tools. Front-end tools, you're going to do schematics, layout, DRC, which stands for design rule check, LVS, which stands for layout versus schematics. A good tool has to have the following features. It's not enough to be able to do each one of these tasks individually. That's not that hard. The trick is to be able to invoke from within the same tool all those tools that will do DRC, LVS. For example, you want to take a window DRC, find out the errors at a small chunk, fix it, do the LVS, or invoke simulation, see if what you have captured so far meets the bill, and so on. This is a far more mature way of looking at it than doing one cell at a time and then waiting until the whole chip is placed and routed, extracting it, back annotating it, only to find out that, oops, let's go to the beginning. That's a lot of time waste. So what we stress in our methodology is that within a front-end tool, and here I try to be as much technology neutral, not to make the presentation a advertisement for Synopsys or anything, but a mature tool has to invoke all those things from the same tool. And this is what we are targeting in this superconducting program. So TCAD simulation, we have predictive simulation and the DTCO part. And as I mentioned, you start from very basic physics equations. I will stress the following. For example, at the stage that we just finished at the end of year one, we've gone and evaluated all those equations. Some of those equations describing how Josephson junctions behave date back to over 50 years old. So what's the big deal? Some equations are simple for calculations, but they're not very accurate for very high frequency. By the time you go to high frequencies targeting 500 gigahertz, you better have equations that deal with the high frequency operations and so on. So it's not a trivial matter in terms of the give and take between cost of computation and accuracy and speed of the tool. So this is in a nutshell where we are heading with TCAD. You have to have a very accurate 3D model of the Josephson junction and also a very accurate equation for implementation, for simulation, for ultra-high frequencies. Post-layout parasitic extraction, I'm going to talk about parasitic extraction at cell level, device level. In this case, the device is the Josephson junction, and at a chip level. What's so tricky about this technology? This technology is all about inductance. Unlike capacitance and resistance, which is a short-range thing that you just look at your next door neighbor, inductance is a whole loop. The return path is very important. So it is very tricky. So first of all, at the level of a device or a very small structure, you need very high accuracy. And that's where you need to have field solvers that will extract things pretty accurately. You cannot use field solvers beyond few devices, beyond a very small region. You need to have lookup tables when you go to extraction at a block level or a chip level, both for capacity, for speed, and you still need to maintain accuracy. So the target is to be able to do RLC kinetic inductance as well as Josephson junction device extraction, all based on lookup tables within a 5% accuracy from field solver. This is our target for the chip level extraction. And then in this picture, I capture all the sub-steps that are needed for this thing. Okay, so front-end tools integration. As I stressed, first of all, the DTCO, Design Technology Co-Optimization, starting with TCAD, and then all the front-end, including schematic capture, layout, DRC, LVS, extraction, and simulation, and all those should be invoked from a single GUI pretty efficiently. This is an example of what our tool is doing in this regard, and we are calibrating it to the available tools in the industry, such as Whiteley, Research, Spice, and so on, and we have almost perfect matching. And this is a situation where from within the tool, which is called custom compiler, we have schematic capture taken all the way to simulation. Okay, synthesis. Synthesis here, we have a big challenge because of many factors. Fan out is equal to 1, as I mentioned, so you need splitters. Also, in CMOS, you're looking for levels. So if you have a 2-input NAND gate, if input A is sitting at 1, you can wait for infinity for input B to reach the level 1, and the output is 1. Here, you're talking a pulse of about less than a picosecond with a height of 2.07 millivolts. And the two pulses better arrive together or have an overlap with a very, very tiny window to trigger a pulse at the output. So this is very tricky, which means path balancing is extremely important. Clocking strategy is extremely important. It's very, very unforgiving. So the question becomes, do you optimize for area? Do you optimize for depth of the pipeline? What do you optimize for? And it's all costly. That gives special challenges for synthesis, including insertion of splitters, including what do you want to do after you do the synthesis. How do you deal with place and route? And I'll be talking about that in a second. But essentially, the synthesis has pretty tough challenges related to path balancing and related to clocking strategy. And different families have different optimization techniques. For example, the AQFP that I mentioned, which is adiabatic switching, lends itself to a special family of gates called majority gates that are very efficient for synthesis. ERSFQ, on the other hand, lends itself to, you cannot construct in it majority gates at all, so you have to rely on XOR-based cells and so on. So we're starting with the same engine that we use for synthesis for CMOS, but with major, major modifications to optimize for superconducting electronics. So the idea in terms of synthesis goal is to minimize the number of required buffers, The buffers here are called JTL, Josephson Transmission lines, and they are pretty costly in area and in power, minimize the number of required splitters, and exploit new gates expressiveness. Again, you have two sometimes conflicting objectives. On one hand, you want to minimize the number of Josephson junctions and therefore minimize the area. On the other hand, you want to minimize the depth of a pipeline because that really impacts the real local frequency at which you operate. And really, we are already reaching the conclusion that for VLSI, you have to follow a GALS approach, which is globally asynchronous, locally synchronous approach. And I will leave that at, I leave it at that for this slide. Here, what I'm trying to stress is that the timing sign-off, this is the classical CMOS, and we're doing the same timing sign-off methodology for superconducting electronics. It's a little trickier than what you might think. It's not a matter of having a .lib file with proper timing characterization and just take a critical path and sum up the delays with budgets for corners and so on. It is much more involved than that because of what I mentioned in terms of arrival times, of concurrent pulses, and so on. So this is in a nutshell. You deal with timing engines within the place and route tool, within the synthesis tool, and generically at a library level. Another thing I do want to mention to you right away is that with CMOS, your load is simple. It's a 2D. On one dimension, you have the loads and capacitances, and the other dimension is rise and fall times. Here, the previous cell and the former cell impact your design or your timing. So actually, I am seeing a note that says my time is ending. So I am really, timing closure is challenging. I'm gonna, power delivery, I started on slide 1 by mentioning to you that you have the challenge of delivering something in excess of 30 amps at something like 150 micro volts, which is big challenge. So you have two types of transmission lines, passive transmission line and active transmission line, which is JTL. The JTL is for very short distances, the PTL for long distances, and place and route is pretty challenging for those. I really want to go straight. These are just layout examples, and I'll go to the summary and conclusion, but I managed to mention all the points I want to cover in this talk. Superconducting electronics is embarking on its own Moore's law. We are roughly where we were at probably half a micrometer in CMOS. Superconducting electronics flow rhymes well with CMOS. DTCO is in its infancy for superconducting electronics, but we aim to make it a major thing to advance the technology pretty fast. VLSI is really hard. If we start with LSI, that's by itself a big achievement. There are some problems that are unique to superconducting, including power delivery, including something that's called flux trapping. And superconducting electronics is a new old technology with vast potential. And let's make VLSI for superconducting electronics happen. And I apologize for taking too much time, and thank you.
We still have a little bit of time. Thank you. We still have a little bit of time for quick questions. We have quick questions.
Okay.
You don't know which ones are quick, but you could assume your question is quick. There's some good with it.
Could you just talk a little bit about the motivations for bringing SCE to the LSI? Is this to do with compatibility with quantum electronics?
You asked a very good question, and I hate to answer it. I'll tell you why. Everybody mixes superconducting electronics with quantum. They are related and not related. If you look at, for example, D-Wave, which is a quantum computer that claims 2,000 qubits, they're using this technology under flux qubits. But not every superconducting is quantum, and not every quantum is superconducting. So there is overlap between the two. The superconducting is a great candidate for quantum because it's scalable, among other things. So, it is a step on quantum. We do have a vision of doing to quantum what we are doing right now for superconductivity, but we don't want to stretch the claim and say this is quantum all the way.
I was thinking that there is discussion that a lot of control circuits for quantum may need to be superconducting.
Absolutely. Actually, now that you brought up this point, a real quantum system is going to have quantum computing, high-frequency classical computing, photonics, and superconducting. The system has to have all.
Thank you. Thank you very much.
Okay, thank you.